The last set of formulas and graphs that we need to study are the hyperbolas. Now, we know how a circle kind of evolved into an ellipse, and now we're going to take a look at how an ellipse kind of evolves into a hyperbola. So again, if you knew the ellipses and you were comfortable with those, let's use that information. In fact, most of this looks pretty much the same. So I'm going to have x minus something squared, y minus something squared equals 1, okay? The only difference really is that before we just added these two. The difference between a hyperbola and an ellipse literally is just one sign difference, one SIGN sign. Let's start off with what is familiar. HK is still going to be sort of like the center, which is this right here, okay? What's different is you could imagine if these two hyperbolas open inwards instead, they would connect and form sort of like this ellipse here. But now they're sort of opening in opposite directions, outwards. But this is still going to be treated like my main or major axis, okay? In fact, it's the only axis, okay? That's almost like a short and fat ellipse turned outwards. So what I'm going to do is I'm going to create that x-axis as my positive axis, which means my y-axis is going to be my negative axis. That's it. Literally, one of my two fractions is going to be a negative, and that's how an ellipse turns into a hyperbola. Okay, A is going to go underneath the positive fraction, and B is going to go underneath the negative fraction. B is not necessarily the smaller number, it's just the one underneath the negative fraction. So if you have hyperbolas that are opening left and right, this is the positive fraction, this is the negative fraction, okay? Now we could do the same thing with my up-down hyperbola. So I'm going to make it look or start off exactly the same as an ellipse, but the difference is instead of a tall and skinny ellipse, okay, these hyperbolas are going to open outwards instead of inwards and connecting to form that ellipse. So again, my y-axis is my major axis, so my y fraction gets the positive, which means my x fraction gets the negative. HK is still the center, okay? And in this case, A goes underneath the positive y fraction, B goes underneath the negative x fraction. That's it. Those are your formulas, okay? Now let's talk about what A, B, and C are. A is still the distance from the center to the vertices. We used to call them major vertices. You still can, but we only call them vertices now, these here, because there are no more minor vertices. Okay, we'll talk about B in just a second. C is still the same exact thing as with an ellipse. It's still the distance from the center to the foci. Okay, so the foci in this case is going to be outside. Okay, again, foci is almost like a magnet point that pulls your parabolas in outward directions, since the foci are further than the vertices. Okay, so the distance from here to here, or from here to here, or from here to here is C. And then finally, B is what we used to call the distance from the center to the minor vertices, which used to look like this, or this, or this, or this. But because those points no longer exist, we just really rename it. We call it the length of the semi-conjugate axis. Conjugate, it's almost like it doesn't really exist anymore, okay? So that's just what we used to call my minor vertices. We'll just rename it, okay? All right, and then the last thing we got to talk about is the relationship between A, B, and C. This case, it's actually going to be the Pythagorean theorem, so it's going to be a little bit easier. A squared plus B squared equals C squared, something we're very familiar with. I apologize, there's one more thing I need to talk about, and that's the asymptotes. Now, the asymptotes used to be really tricky, but I'm going to make it as easy as possible for you. Let's go back to point-slope form in Algebra 1 real quickly. Hopefully, you guys remember from point-slope in Algebra 1, it's going to be y minus y1 equals m times x minus x1. So we're going to set up that structure, okay? So we're going to have y minus y1 equals the slope times x minus x1. Same thing here. Y minus y1 equals the slope times x minus x1. Okay. What the heck are y1 and x1? Same exact numbers you have here, so you can't really screw that up. So your standard hk, just be careful. Make sure h is with the x and k is with the y. And the last thing we got to talk about is the slope. So I'm going to make this as easy as possible. Once again, we learned from Algebra 1 that the slope is always y over x. Technically, it's change of y over change of x. y2 minus y1 over x2 minus x1. So if you can remember y's are always on top and x's are always on the bottom, that's going to make this extra easy. What we're going to do is we're always going to take the denominator of y over the denominator of x. So in this case, it's going to be b over a. In this case, since a and b are switched around, it's always y, which in this case is a, over x, which is b. Okay? So if you know these formulas and you know a, b, and c in their relationship, then solving these shouldn't be too bad.